This computer, okay. This time.
I'll do those slides.
Yeah. Well, hello, stargazers. Studying with cosmology. We love this particular branch of science. I do. And another stellar program from John Winkowski. Astronomy programs manager. I got that down. My name's Ron here. I'm your vice president. People me for this last month, and maybe you'll re-elect me. We're about to do the elections. We got several things we're going to do. We're going to go fast. This is a rare night for all of us here at Seven Redstone on the Olympic. Because essentially, we know we the professionals, we leave it up to our crew, the people in the club, and we found out one, not two, three. And not one of them was an officer, because in years past, when we didn't get enough, get one volunteer maybe. Jerry, our president, who was on the screen. Sorry. That's all right. Reminds me of that guy in 1984, there at all those meetings, looking down, like exalted ruler. Get my glasses. I'm still trying to get to on my screen. And oh, he's on yours too. Yeah, I need my glasses. Well, we're still in the planetarium. Old man Gladwin turned over in his grave, wherever he is, whoever that was. Standing beside me is one of the past presidents, who is now our webmaster, and Tom Totten. When I first joined the club about 7 years ago, used to do his running the meetings from right over where Chuck is standing on the edge without a microphone. And you know what, I'm trying to remember what Jerry was doing. I don't think he was an officer, was he? But he was here. Can we make Jerry talk? Tell us before he is. I assume you can hear me. You can look up my nostrils and say to you. There's Jerry on the screen to our left.
Can you hear me?
You hear you fine? How are you?
Your voice is, all the sound from your end is heavily distorted.
Close. I should have come through the laptop, I would think. Okay. How's my voice sound, Jerry? I guess it doesn't work.
No, it sounds like heavy harmonic distortion.
Oh, great. Great. What you're saying is it sounds typical for the hookups we always have.
See, I didn't pick up a single word of that.
Wow. Okay. Well, okay. We don't need you guys. Let's go back to our program.
Okay, I think that's my comment.
We have 4 things to do tonight, and Jerry's part of it is our week with Zoom, and it's all being archived. There's a crowd. I think it's more than half full. I personally like it better down here in Farrand Hall. Nothing against that big Fleischmann. We had a huge crowd in here back in April because of LCO, which is Las Cumbres Observatory. They have a huge network of their own. And one of their speakers was booked, and the lady that filled the bar down in Lower State Street with astronomers in the back. Only filled the room here. Good thing the fire department never got us that day. We're going to elect two people are up for 2 of the officers. The other 2 are James presidency and me and the vice president with the I want to say the descendants, the incumbents. And George Santos, so never mind. It's coming up. Yeah, that's what we'll do first. That's right. Before we get to our not 1, not 2, but 3 incredible talks. So I'm going to play video, find about meteorites, tektites, whatever those are. And incidentally, make a note about seeing Chuck McPartlin's incredible collection of their meteorites, including the dreaded 5-pound older than dirt that he takes to our second Saturday party that'll be next weekend. Next meet. Okay, who's ready with his contingent? Talking about meteorites, that'll be followed by Rex Meach. From there's Rex with his lovely wife, Stevie. And he used to
navigate by the stars. When we brought a sextant, I asked him to. I have no idea how it works. They demonstrate. In the front of the mine, Astrophotography. He and his son going to step off the program. All the each of you will have 15 minutes. If you go over by 5, that's fine. We may have some questions. But first of all, we want reports from the different members of the board who got elected, appointed, and of course, our really beloved outreach coordinator, Chuck McPartlin. Do I start with you or Pat? Not first. And he was also a candidate. The only one for according to our treasurer's job. Okay.
All right. Okay. Thank you. All right. I have a little cheat card and it says thank you, Jerry, but I have to say thank you, Ron. Hello, everyone. My name is Pat McPartlin. I'm the merchandise manager, the merch manager, and I've got some merch up with me. We have a fantastic mug, and I have a bunch back in the corner over there. These are $10 each, so that's a good price. And we have our wonderful tote bag. That's only $20. This thing is amazing. I've taken it on airplanes, but after TSA, you can put the water bottles in. But it's zippered top, and then it has a place for your magazines and your newspaper that you want to take on the plane with you. But only $20. It's $50 in Staples for other people's. Wow. And then I have tonight dancing and all sorts of pleasure. This is our blanket that it also has our logo on it. It retails for $30, and tonight it's only $20. It is a light blanket, so I have 3. So go ahead and buy all 3, and then you'll have enough warmth. As you can see, we have all kinds of goodies in our merchandise cabinet, you might say. I don't ship, but I can meet you someplace in Santa Barbara. Let's see. Yeah, all the prices are there. My email address is merchmgr@sbau.org. So just let me know what you'd like. All the sizes are true, so if it's extra large, it will be extra large. But the blankets are all one size. Okay, and back to you, Ron.
And I know you're running a tight race, and a lot of people want that job, so good luck in the election. I call him Captain White Brim Hat. For years, he's held a job, and he's done a good job, and that's the one later on we'll talk about that runs the money situation here. And he's been trying to get out of it, and finally she stepped up and volunteered, and she's the only one ready who will vote for him. Or if it's too late to field the nominee, that's over. Are you okay, sir? Technically.
Not really.
You're in California. The president of California. I wanted to ask you where he is. You get distortion. Or is it starting? Is it me? Probably is. Okay. Part of the incredible club in Santa Barbara, which has been here since 1955. Back then it was called the Santa Barbara Star Cluster. Someday I'll tell you the quick history I learned from this man standing next to me. Yep. Chuck is the man himself. He is the heart and core. Can we bring him on?
And there's even a free patch here to tap.
Okay, hi everybody, thanks Ryan. Yeah, quiet outreach this week. It's just the normal monthly things. The schools seem to have realized that it's always raining during December when they schedule something. So they're going to start up again January, February, it really will rain. And so we have our second Saturday, next Saturday on the 9th, 7 to 10 for the Star Party here. And then the 15th, that's third Friday at Westmont College. Observatory.
And then fourth Tuesday, Telescope Tuesday Community Around Marketplace on the day after Christmas. They'll probably still have their big Christmas tree up, so we'll set up our telescopes around that. And for 2024, Telescope Tuesday is going to move to the second Tuesday of the month out there at the big box because there's so much light pollution that we try to maximize the number of first quarter moons we get during the course of the year. So that's really all the outreach news. I don't have the summary yet of the year. I'll have that for January. It looks like we've had a roaring comeback after COVID. Our star parties here at the museum have had 300 and 500 people showing up for them pretty regularly. So it looks like it's going to be a good year. So thank you.
As far as I'm concerned, he is the heart of the club, my friend. He's been around longer than anybody. Probably held most of the offices here in the club as well.
Right now.
Ah, is that what's on the screen? What I'm looking at? There is the Palmer Observatory. I don't know who Mr. Palmer was either, but we're looking into it. Before the pandemic, you know, we were supposedly out doing outreach 200 times a year. That's more than half the week. Yeah, that's a lot, but not that many nowadays, right?
It's, I think we're hovering around 180 this year. So.
I don't know how you do it. Well, next week, of course, is the big one. Once a month, the museum even puts out the word about our star parties. You're all invited. Show up. It's next door, next to the observatory. Reminder: nobody does more outreach. We have some things I want to tell you about real quickly before we do the election. Tuesdays for many years now, there is an online show that has been run, having nothing to do with me. I was on once, but Jerry, the president, is there, and Tim Crawford, one of our obviously well-suited lens experts. They grind, they make telescopes. It's just an incredible program called The Workshop. That'll be Tuesday night. Monday morning, we have the SBAU Astro Hour, and we'd like to invite you all to join us. You can watch on YouTube. Just remember SBAU Astro Hour, 11 to noon on Monday mornings. I'm your MC. I'm the guy that doesn't know anything, surrounded by the likes of Chuck and Jerry and the ones that answer my questions. And it's like taking a course out at Broida Hall on the university campus, where every week there's something. Here's my theory about this incredible science that we're involved with, gang. Up until just recently, I thought, you know what? Of all the sciences, this is the one that people like the most and gets the most news. And because every week there's something, there's a launch or a discovery or an asteroid heading toward Earth. But then I realized, no, there's another science that's bigger than us. That would be medicine. Thanks to the virus and the pandemic. However, we're a close second, and we're very, very, very happy that everybody loves it, and it's mostly good news. So the Astro Hour, I'd like you to tune in. Are we ready? Here's how we're going to do it today, folks. First of all, let me tell you what we're going to be voting on. Members only. The president up for another year. He's been in office with us for 6 years, I do believe. I came in a year later. We lost the young man who was vice president to Caltech. His name was, what was his name? Lopez, Adrian. And proudly, I'm in here as VP, the old heartbeat away guy. I get to run the show when Jerry's out of town. And then we've had, as we said, Colin Taylor run the Treasury Department, happily giving us the figures, where we stand, how much money's coming in, going out, approving things. And then the secretary has bounced around a lot. Is Tessa here? She was willing to do it. There you are, Tessa, thank you. Your health is getting better, and someday you may be in that seat. If maybe next December you're okay, and we'll be voting for you. Andy Allen is a young man who is running for secretary. Is that you? You did make it. All right, Andy. Not only candidates for secretary. Did you see, were you in the planetarium? Did you see the show? Oh, okay. He was so good that last month, when we had Matthew, the guy from our speaker, you were taking notes. I don't know what you did with him, but it wasn't like a meeting, but it's good practice. I noticed, I was sitting with him. What I want to do to run this and get it over with quickly is have everybody in the room that is not a member of the club yet, although we're not going to twist your arm, but it'd be nice to have you on board. If you're not a member, raise your hand. Okay, that means the rest of you are members. So I would, including, if you are a member, would you stand, please? And remain standing as we go through the votes, okay? This way, only the people that are standing can raise their hand. Let's see if we want Madam McPartlin, Pat, to take over a job starting in January as our treasurer. Raise your hand. Well, that looks pretty damn unanimous to me. Okay, you are the treasurer as of now. Andy Allen as secretary for a year at least. Okay. Okay, everybody. You want to re-elect me as vice president? Will you have the tenor? Like Groucho used to say, I wouldn't want to be a member of any club that would have me as a member. You know? And last but not least, and I don't know why he's not on the screen, but just as well. Let's see, he's up. Was he up there? Oh, hello, Jerry. Can you hear me now? Jerry Wilson for president. Since nobody's running. Okay, you guys can sit down. The election is over. Amazing how easy that was. I thought it would be a problem. You want me to read all this? See, Santa Barbara Astronomical Unit 2024 elections. All right, state of the members who volunteered. You got the president. Oh, thank you to our other volunteers. Oh, that's right. I just learned her name. I don't know if she's here or not. The new event secretary or an event coordinator. Oh, let's give her a hand. What's your name again? Diane. Oh, it's there. Okay, good deal. These are the appointed positions. However, if you want to run for those, you don't get elected. You just twist some arms and dole out some cash or whatever you want to do. And then Chuck runs outreach. And Madam Treasurer, you're going to remain Madam Merchandise. And then you both give up the secretarial job to newly elected Andy Allen, who can't be retired like the rest of us. Andy, what do you? Well, you're awesome. Can't wait to have you taking notes next to me. Who else is up there? Let me read the screen. Thanks to our Museum of Natural History Astronomy Programs Manager, John Winkowski. Gave a great show. Down with a cough or something for about a week and is gloriously reliving those old days of the pandemic by wearing a mask again. Members are encouraged to volunteer to help out at all these positions. So thank you, and we'd love to have you non-members join us. If not, you're more than welcome to come to meetings. Next Saturday night, of course, 6 o'clock, right? It'll be dark by 6. 7 o'clock. We get there at 6 to set up. Okay, then let's have our speeches. And we got 3 great ones. These are the gentlemen. They're in the club, and I'm going to introduce you to them one at a time. Earthquake Dave Feinberg used to run this program. It was an hour show, and he got paid for doing it. And he made money on the side talking about meteorites and tektites using an old carousel projector, a slide projector. Back to use those slides, and they got turned over to PowerPoint. He has a geology degree, loves teaching about nature, worked for me for a while as a DJ, believe it or not, a mobile DJ, and had a grand time. And this was back in the 80s. And he's got his slides ready to go about tektites, whatever those are, and meteorites. Dave, come on up, take over. Let's give him my hand. Let's stay up here, I think. Okay, watch yourself blow the cords in there. All right, yeah. How are you gonna put it? Just where? Yeah, right here. Control? Yeah.
Let's see. Let's stop sharing this one and go to our new share screen and hopefully that works. So it's been a little sticky here at the remote control for some reason.
This is why I had a pre-Cambrian slide projector with the carousel, and you push the button and the slide comes down in front. But I had to digitize this one. So Tom was nice enough to come over and I shined my slides on the screen. Ready? On the screen, and Tom was nice enough to come over and take pictures of it with his phone. So no one's ever seen these slides or these photographs on a wide screen. So let's see how well they came out. Now, I did the slideshow in this room on that screen, the full length one, about 15 years ago. And one thing I learned pretty quickly is there's people in the club that know a lot more about this than I do. For instance, Chuck. And Chuck was nice enough to bring some of his meteorite collection. And so after the program's over, after the meeting is over, he'll be up here to share about the universe due to his with his meteorites. Here, watch this. Look at me, I'm holding a piece of outer space. Is that right?
Dave, get behind this.
Get on the mic, on the lens.
Look at me. Here I am holding a piece of outer space.
That's the older than dirt bottle, right?
Yeah. Look at me. I'm holding a piece of Mars. It's a Mars meteorite. And so when Chuck's here at the end of the meeting, he can explain to you how you know it's from Mars. Okay, ready to go. Now, this is the man who sitting right here was for many years he was Baron Ron Heron, now our vice president, who was also he's a radio personality. He's also Baron Ron Heron's mobile discotheque. This is the Baron and myself 35 years ago when he was training me on how to show people a good time at a party with music. I wasn't sure what to make of him at first, but as it turns out, he's a good guy. This is a 15-minute version of a 45-minute slideshow. I eliminated a lot of things. Meteorites. Sometimes they hit hard, or sometimes they break up and just fall down from the sky. When they hit hard, it's hyper velocity, like 20,000 miles an hour or more. A lot of bodies in our solar system show they've been beaten by meteorites a lot. For instance, the moon and Mercury. And so what that shows is they've been beaten by meteorites for billions of years, and there's no atmosphere or water cycle to erode them away. And like on the moon, sometimes a meteor will strike and they'll be melting because of the heat of it. And so lava flows will come up on the surface. Like the big round meteor strikes on the moon are later filled with lava. And of course, Mercury too. No atmosphere, but been beaten pretty bad. And also the Earth, assumably, was hit as much as Mercury or the moon, but we have a water cycle and an atmosphere to wash them away. Right, very good. Erosion. Right. Well, not to scale, but Earth here and there's the asteroid belt between Mars and Jupiter, and a lot of them are assumed to come from there. These are some of the larger asteroids in the asteroid belt. And the way it works is with the way gravity is, any piece of matter more than 300 miles wide will self-gravitate into a sphere. See, a lot of cameras in national parks. Someone caught a meteor struck across the atmosphere there at Grand Teton. Now, that's what it looks like in broad daylight. That'd be quite the fireball at night. Sometimes it skips off our atmosphere back into space, and sometimes it breaks up and pieces of it fall down. But that would have been something to see at night. If you're ever on your way to the Grand Canyon, there's Meteor Crater National Park, National Monument. Here's a visitor center, and it's about a mile wide, 1,000 feet deep. About 10,000 years ago, it had a hypervelocity strike straight down and made that big crater. And because it's in the desert, it doesn't erode away much. It's still in pretty good condition as far as how it originally looked. And it's south of the Grand Canyon, a must see if you're an astronomer. Here's another view of it. So what happens when geologically, when something strikes like that, you'll have a lot of broken up material from the rocks and rock formations it hits down to the crystals of the minerals of the rocks. It's called cataclastic texture when something hits and breaks everything up like that. And we have an iron meteorite. A lot of people go around looking for them with metal detectors. People still go there and find them. There's another meteor crater in Canada. This is the vocabulary word for the evening. The technical term for a meteor strike feature. Anyone know what they are? What's it called? It's called an astroblem. So it's a blemish on the face of the Earth, and Astro after the pet dog of the Jetsons. These are known meteor strike features on the surface of the Earth. And so there's a number of them, over 100 of them that we've recognized, some in different stages of erosion. This is a 1962 Chevy Malibu, and it was hit by a 28-pound meteor. Now, how cool is that to have a car like that if you're an astronomer? I don't know if insurance would cover it. I wouldn't fix it. If you're driving along and you get pulled over, sir, your tail light is out. I know, I got hit by a rock from outer space. Sir, you see, please step out of the vehicle. Nowhere is safe. 1954 in Alabama, a meteor came through the roof of the Hodges home and hurt her. The only person ever known to be hurt by a meteor. Ann Hodges. Now look at the precision of this. Within 4 inches, this meteorite has been flying around the universe for billions of years, for billions of miles, and it came down to 4 inches. And 2 inches one way would have missed her altogether, and 2 inches another way, she would have gotten really hurt. It left a bruise, not a scar. That reminds me that I've been wanting to lose some weight. I think my meteorite exposure is too high. This is a drawing of a meteorite that hit the Earth in Germany about in the 1500s. And it was taken as a sign from God to stop a war. And so it was profound enough to cause everybody. There was a Tunguska meteorite that went across the sky in Siberia, and it had an explosion such that shockwave blew out windows and injured people, and it's certainly enough to knock you off your horse. And so anyway, they made it so it ended up ending the war. And there it is, with the keepers of the meteorite. This is an order of people that have been charged with caring for the meteorite that stopped the war. Now, I like those outfits. See, we have T-shirts and sweatshirts that you showed. How about something more like that in our catalog? People would take notice. Yeah, right. And you can toast things. So anyway, meteorites seem to draw people to want to see and touch something as old as the Earth. And you have to go where they are to find them and bring them back. Those iron meteorites are pretty heavy. And one thing about the bigger ones, you don't have to worry about anyone stealing them. I mean, that piece of machinery would wake up the whole town. Now, this is the largest meteorite I've ever touched. I was in Copenhagen doing in the 90s doing a Eurail trip, and it was the miserable weather. So I looked at the map, and they actually have a geology museum in Copenhagen. So I went there, and this was sitting out front. Turned out they're having a world conference on meteorites in English. They made a day of it. This is the largest meteorite ever found, and is presently on display right where it landed. One place that's good to find hunt meteorites is on Antarctica, near the edges of the glaciers. You see, the meteorites strike all over Antarctica, but the glaciers, being an active feature, will concentrate them along the edges. And so you go around the edges and they're really easy to spot. It's like this dark spot in a light ice. So anyway, a lot of people go there to look for them.
Not clicking.
Okay, something happened. All right. And a lot of science is done with meteorites. For instance, the Mars meteorite, we know it's a Mars meteorite, one from its age and one because of the trapped gases in the minerals. Now the meteorites, most of them are stony meteorites. About 80% of them. 10% of the ones are iron meteorites, but most of the ones we find and see are iron meteorites. A stony meteorite just looks like a rock, and metal detectors don't pick up on them. But stony iron meteorites, and then ones that's even a little more rare than that are stony irons. And so each meteorite has a lesson to learn, things to. Each one tells a story about the history of our solar system to one degree or another. Now, this is a catalog of meteorites and that people can buy, and they sell them by the gram or by the ounce. This is a Mars meteorite. That one there. By the way, the Hodges meteorite that hit that woman a few years ago is selling for $750 a gram, which is times 28 grams. That's $20,000 an ounce, 15 times the price of gold. And the one that hit the Chevy, that's $150 a gram. I don't know if it hit a Ford, would it be? How about hitting a Tesla? I don't know. I don't know the story of it.
It was actually in 1998. Heat skill meteorite, and that was a Chevy Nova, and it tripled in value.
The Chevy did. Okay. Okay. Button problem. Okay. Move along. Mars meteorite. Where it came from. So this is looking through, paging through a catalog of meteorites for sale. Should I point it at something in particular?
No, it's got either delay or just keep giving clicks and every few seconds see if it catches.
There's actually a large variety. There's carbonaceous chondrites and so for people that are interested in them, all different kinds. It behaves once in a while.
Use the keyboard direction.
Okay, is there something I can do on this?
Try the right arrow, but.
Right arrow.
The arrow keys. But it's been kind of hanging up on that.
It's been doing pretty good thus far. We have a tradition in the club that something always has to go wrong a little bit. Okay. Hey, tektites, but I think that's for another day and another time.
Are you only halfway through?
No, I mean, most of the way through.
Well, a couple of questions from me. Why bother NASA bringing back those samples? We've got it all right now. Here's a question I have for you that you probably know the answer to. I know Chuck will, but I'm curious about you. What's the official rule about rock falling in your area? Who gets it? Anybody know what the law is? Finders keepers if it's on your property. Yeah, all right. In other words, if you have a shop that you're renting from somebody, the landlord gets it. If it's on government land, goes to the Smithsonian.
Okay.
Learned that the other day. You did very well, my friend.
And so, I went back. Very well. Oh, I was gonna say, after the meeting, Chuck will be up here to answer your questions and entertain you. And who needs Google when you have a Chuck?
That's right. Chuck brought some of his meteorites, right? got a whole bunch of stuff, thousands of dollars worth there. This is your honorarium, incredible cup, our classic cup for our members.
Next show on. This thing is just not consistent. Dim the lights down?
On the next one, please.
Yeah.
Thank you.
Let's see,
That
okay.
one came out pretty well because you take it off the screen.
Okay, so-
Well, I'm gonna need this, I got to see to read,
Yeah, gonna, yeah, give the Baron some light here.
and we want to see our speaker. There we go. Is there a in between?
Suppose you can read your thing. Go to,
Whoever's via iPhone has their hand raised.
I think that was for voting.
Okay.
Thank you, vote attendance.
I didn't understand that, but is it possible to stop halfway between?
I'm working on it.
Okay. Because Rex is here and brought his wife, and he's the only members from Ojai we have, and the man used to.
How's this?
Yeah, that'll work. That will work. All right, as he comes up, Celestial Navigation from Ojai, a graduate of Nordhoff High School graduate, married to Susie for all these years. I'll let him tell you. Got his biology BA in 1970, went into the Navy, same year, served on the USS Safeguard and kept them sailing using celestial navigation with the stars, I guess. Ray is a medical, ran a medical lab for Mayo Clinic, and he's an insect ecologist, among other things, but that's not what you're just.
Well, it was a second job.
Okay, well, look, here's, you press the button there. If it works, that's yours, Rex.
Then-
Let's give him a hand. The man is gonna do a good celestial navigation.
See, I've got to be in the uniform of the day to get put on report, you know.
Well, that's not what you wore on the Navy ship, is it?
Well, not exactly, but let's see.
How long has it been since you did this?
Well, 50 some odd years.
If you remember enough to talk about it.
Well, I had to review it a little bit. But,
Okay.
okay. And here's the clicker. And you can
It's the same thing on the screen. in front
see
of you.
the confidence with
Right
which
there
the
on the
navigator
left-hand screen
approaches
is the
his
same thing.
task.
Okay. go
Same
ahead.
thing. And
Yeah.
if I click it there, it will,
it should.
okay.
Good luck. Big one.
Okay, well, I haven't given a public address for decades, which means I haven't any experience with modern presentation software. So I want to thank Tom for taking my sketches and putting them into a PowerPoint compatible setup. Thank you, Tom. Appreciate it. Welcome to Celestial Navigation Oversimplified. What I'd like to do is take you through a procedure for finding your position on the Earth's surface using only a sextant, a chronometer, a book of astronomical data, and another book of trigonometric functions. That is, no electronic anything, no internet, not even a hand calculator in those days.
No GPS.
No GPS. Texas Instruments and HP were going to come out with hand calculators within a few years, but we were just before that. So I learned this in the Navy in the 1970s. And at that time, we actually had an electronic navigation system called Loran, and it used carefully timed pulses from ground-based transmitters rather than orbiting satellites like GPS. But I can tell you, after spending many frustrating hours sitting in front of a Loran set, that it was essentially useless to us. What the larger vessels might have had available, I'm not sure. carriers and submarines probably had better equipment than we did, but for us, as soon as we were out of sight of land, we were as dependent on celestial navigation in 1971 as Captain Cook had been in 1771. We weren't doing it for play or practice. It was our essential way of finding our position. Of course, you've had now several decades of GPS, and it has made celestial navigation unnecessary as a practical matter.
He's trying to get the speaker view. I don't know why Jerry's getting all the fame here.
Oh yeah, we do have other Zoomed people.
Yeah, there we are. This is what we want. Is Zoom.
Non-speakers.
See if I can hide them. That's to
Hide non-video participants.
perfect. Now is he come up on top now?
Yes.
Yeah, okay, let's try that. But I can go back to single speaker. Okay.
Okay.
First come, first serve, I think it was.
Yeah.
You were saying, sir.
What was I saying? Oh, yes. Okay. And GPS, of course, is several orders of magnitude more accurate and vastly easier to use. So, well, why talk about it other than to, fill some space for Ron? Well, I think there are a couple of reasons. And first, practically everybody in the world knows that sailors have found their way around using the stars for hundreds of years. In fact, it started in rudimentary form with the Phoenicians about 4,000 years ago. But almost nobody knows how they actually did it. And I thought that people who are already interested in astronomy might enjoy learning in a little more detail how you actually do this thing of finding your way around using stars. And the second reason is that this group is very well situated to experiment with this hands-on. If you have a telescope that can report to you the elevation of the target it's currently trained on, you can investigate celestial navigation yourself. You don't need a sextant, and you don't even need an ocean. You can record the data, go through the various site reduction methods that might be of interest, and plot a fix, see if it shows up
Just get the arrow out of the way.
yeah, where you wanted it, and you can, in other words, you can participate in this, not just learn about it. I've got a few notes here that are.
You brought a sextant, didn't you?
I did bring a sextant, Ron, and I wasn't really going to go into it because I thought it was more important to know what you do with the numbers you get out of the sextant than how to use it. There just isn't really time to,
Is that what the cartoon captain is looking at?
That is indeed a sextant,
Oh, okay.
yes. Anyway, if you ever try this out, if you use the data from your telescope and you get a pinpoint 3-body fix that runs right through the center of your backyard where you're set up, it can be kind of like a minor triumph. It's actually a lot of fun to do, and the fact that we have GPS is just, well, GPS be damned, it's fun to do. Okay, celestial navigation is underlain by a very simple theory, and amounts to little more than drawing part of a big circle on a smaller piece of paper, a piece of paper too small to accommodate the whole shooting match. And maybe I should repeat that, because everything we do from now on in this talk is going to be about drawing a circle. Your object is to accurately draw a segment of a circle on a smaller piece of paper, and that's about all it amounts to in its simplest form. Unfortunately, there are frustratingly many details to be attended to before you can actually do that. And there is a whole specialized vocabulary and a small ocean of acronyms associated with this art. And I'm going to try and skip over all of that. Now, I want to find out, is anyone in the audience a navigator already? Anyone here familiar with we have one?
He's asleep.
He's not listening. Well, then I don't have to do my disclaimers about height observed versus height sighted and about
I did celestial navigation back in 1963 when I was a teenager.
oh, well, then I'm going to for instance, I'm going to be talking about geographic position of a celestial body, and I'm going to give it in terms of familiar terrestrial coordinates, like I'll be referring to the longitude of the geographic position rather than GHA, and latitude instead of declination, and so forth. So you'll just have to forgive me for not using formal navigational parlance. If I tried to do that, nobody would know what I was talking about. May have trouble anyway, but okay. We'll look at a handful of concepts, and the first couple will be theoretical concepts. And then we're going to look at the setting within which these ideas are applied. And then we'll actually go on to the procedure for plotting a fix. So the first, let's see.
Push the big button.
Push the big button. I've hesitated to even include this, but just in case, a quick reminder that every point on the Earth's surface can be uniquely identified by giving its coordinates in latitude and longitude, where latitude lines run parallel to the equator, and they're measured from 0 degrees at the equator through 90 north and south as you move poleward. And longitude lines run from pole to pole. They're measured from 0 to 180 degrees east and west, starting at the Greenwich Meridian. So much for our review there. Whoops.
You might want to say longitude is each hour of the day is the longitude line, isn't it? The longitude lines.
Yes, they are associated with time, but yeah.
Okay.
Okay, the next idea here is the nautical mile. We use a mile of 6,076 feet instead of the familiar statute mile of 5,280. And one might ask, why have two systems? Why confuse things? Well, here's the reason. If you consider any 2 points on the Earth's surface separated by 1 degree, here you've got point 1, point 2, and they're separated by 1 degree, measured at the center of the Earth. If you zoom in on that, here's our 1 degree. That angle will subtend a distance of 60 nautical miles measured along the curve. And because each degree is divisible into 60 minutes of arc, 1 minute of arc is equivalent to 1 nautical mile. In other words, the angular measure and the linear distance are numerically identical, and that's going to come in very handy. Okay, Next, click again. Okay. Geographic position. If you extend a line from the center of the Earth out to a celestial body, it's going to emerge from the Earth's interior and head off into space at some specific location on the Earth's surface. And that location, of course, like every other location, is going to have a latitude and a longitude. The only problem is that the Earth is spinning. And so that point is constantly changing. And if you're considering a geographic position at the equator, that point is moving at 1,000 miles an hour, or about it's about what, a quarter of a mile every second. And for that reason, whenever you take a celestial observation, you need to also note the date and time to the nearest second that you took the observation. Okay, where do you get this geographic position? Well, I mentioned that we have a book of astronomical data, and here's an example of it. This is for the upcoming year. It's published every year, and using the Nautical Almanac, the name of the book, for the sun, the moon, Venus, Mars, Jupiter, Saturn, all of the first magnitude stars, and quite a few of the second magnitude stars, depending on who's publishing it, because there are various companies publishing. It will give you the geographic position to every second of the year to the nearest 1/10 of a minute of arc, which is about 200 yards. Okay, so that's the geographic position. And let's see, is our advancer here. Okay. The next thing we need to talk about is called the circle of equal altitude. Here. If you were to stand at the geographic position of any body and stop the Earth from rotating, it'd be right over your head. And if you took out a sextant and measured its height above the horizon, and the sextant, that's all a sextant does, is measure the angle between the horizon and the celestial body. If you were standing at the geographic position, your sextant reading would be 90 degrees exactly. If you walk away from it in any direction, 1 mile, repeat the reading, you're going to get 89 degrees, 59 minutes. If you walk 2 miles away, you'll get 89 degrees, 58 minutes. If you, well, you might want to drive 60 miles away from it, you're going to get 89 degrees even. So basically, for any given radius, there will be a circle. And anywhere on that circle, you will get the same sextant reading. Doesn't matter where you're located. You're going to read it there, read it there, read it anywhere. You're going to get the same reading. And that is called a circle of equal altitude. And the way you find that radius is really simple. You just take the number 90, subtract your sextant reading from it, and that gives you your distance, assuming you convert everything to minutes of arc. And well, let's see, we'll do an example here. Suppose that you measured Antares, and it was 23 degrees, 47.2 minutes above the horizon. Subtract that from 90, you get 66, 12.8. convert the 66 degrees all into minutes and add the 12.8, you get 3,972.8 nautical miles. That's how far away you are from that position. Then you know that position to within 200 yards. So now I know that I'm exactly on that circle. The only problem is that particular one, if you look at that radius, this is about 25,000 miles around. So it's you're not being quite usefully precise with it. And for that reason, you have to have at least two bodies to get your more exact position. Let's suppose that at the same time we did Antares, we also measured the neb. And of course, it's going to have its own geographic position. It was a different height of eye, so it has its own circle of equal altitude. And the only way we can be on both of them at the same time is to be at their intersection. And you'll notice that we've got two intersections. That's not really going to cause us much of a problem. This next slide sort of illustrates why. It's pretty clear. Well, you can be reasonably confident in rejecting this as a possible position. In fact, you never in practice have any ambiguity about the intersections of the circles. Okay. So you need two bodies. Well, I think that's enough theory for the moment. And what I want to do now is show you the setting. And it turns out that Captain, what is his name? James Tiberius Kirk and his engineering officer, Montgomery Scott, have got a brand new teleporter, and it has the time travel enhancement, which they got at no extra charge. And Scotty's going to beam us out to April of 1971 aboard my old ship, the USS Safeguard. And let's see if we. How do you determine the distance between the two centers?
Oh, you don't need to know the distance between the two centers. Because of the you
change the intersection a lot.
Yeah, well, it would, but you don't in fact end up needing to do it. You work them both. You'll see in a minute how it works. Oops. So there's the Safeguard in all her photogenic magnificence, inspiration to maritime artists throughout the ages, I'm sure. What we're interested in is at the chart table, and let's say that as we come aboard here, that we are say 2 days outward bound from Pearl Harbor en route to Guam, and we're steaming southwesterly on a course of 220 degrees at a speed of 10 knots. And we're going to look at the chart table. Actually, let's look at the form that will be on our chart table. We're going to use someone else's just by way of an example here. What you've got is called a plotting sheet. You use some variation on this all the time you're at sea. They're published with, you have 3 drawn latitude lines, which you supply the labels to. The publisher has no idea what part of the world you're going to be. It also comes supplied with a central meridian that you have to draw in your own additional lines of longitude. And there's a very simple procedure for getting the spacing right. Obviously,
since the lines of longitude converge as you go toward the pole, you can't publish it in advance. You have to set it up and use it. And you mark in your lines, even, integer values of longitude. You've also got a protractor on here for measuring angles. You've got this gizmo here, which is a longitude scale, again, compensating for the fact that these guys are going to be closer together as you go forward. And notice here that you've got.
Rex, I think I need to get you back behind the microphone just for the people home.
Oh, yeah.
Zoom, sorry.
You've got the central meridian labeled with 60 divisions, 60 minutes of latitude. So you're at. Oops.
Not clicking forward.
There we go. You're 47. This would be. If I can see it here, well, can't really read where the 30 is, 47 degrees, 30 minutes, I guess. I can't quite read that. 30, 47, 35, and so on. And those are also, remember, 1 minute of arc is good for 1 nautical mile. So that's not only a scale of minutes of latitude, it's also a scale of nautical miles at the same time. And you've got 60 nautical miles here, you've got 60 there, you've got typically some at the top of the bottom, top and bottom. So what that piece of paper represents roughly say 180 miles by 180 miles. It's a patch of ocean. Okay. It's about 18 inches on a side, and you're going to use that to do all your records. So let's redraw this. We'll go back to the safeguard and leave off the longitude scale and the, all of the other stuff here, so we don't confuse ourselves. We'll leave only the latitude and longitude grid. And this line here, what is that? Well, that's called a dead reckoning plot. And basically, you're on a course of 220, we said, you're at a speed of 10 knots. You're moving in this direction, and you have labeled it with your position at different times of the day. And this is always to some extent a fiction. This is what you do is you project this out and you say, well, by whatever that is, 1800 hours, I'll be approximately there. The reason this thing is only an approximation is that every time a swell comes under the ship, she goes a little bit off course and the helmsman has to correct. So you're oscillating around 220 degrees. You hope to make that good on average. Your speed is also going up and down for the same reason. So this is not constant. You're subject to currents that are flowing in unknown directions with unknown speeds. So this thing starts out pretty reliable when you get your most recent fix, but every passing hour it grows less reliable. And in our example here of aboard the Safeguard, assume that when we left Pearl, it was under a dense cloudy sky, and we're now 2 days out without ever having a celestial fix to correct it. So let us, pardon me a moment here.
Gonna give you 5 minutes, my friend.
Anyway, this guy is, let's assume that we are going along and we've just shot our first celestial fix, And we get, bear with me a second here. I think it's this next one. Yeah. Let's suppose that we've taken around the sites now, and we recorded the date and the time and so forth. And one of the sites we took was on Regulus. And we got an elevation with the section of 34 degrees, 47.3 minutes. And so this is what we're trying to do here. Here is the whole world. Here is the geographic position of Regulus. Here is the circle of equal altitude. And this little square here is our plotting sheet representing around 180 by 180 patch of the Earth. And the thing we're trying to draw is this little segment here of the circle of equal altitude where it passes through our plotting sheet. Okay. We'll zoom in a bit. Here's a little higher magnification. And the point I want to make here is that the curvature of the circle of equal elevation is so gradual, so gentle, that the little segment going through our chart here that we're attempting to draw can be approximated by a straight line without any loss of accuracy. Let me see slide here. So how do we draw it? And this, it gets a little touchy. The way you draw it, how do you start drawing that circle on that piece of paper? Well, you choose a position near where you think you are, called the assumed position. And you measure its longitude and latitude coordinates. And you're going to use those coordinates along with the coordinates of the geographic position Regulus. And you're going to go into your math tables, and the math tables are going to produce two different numbers for you. The first one is going to be the azimuth between the assumed position that you just decided on and the geographic position of the star. In other words, this is the direction you would have to walk if you wanted to stand directly under Regulus at that point in time. Okay, the next thing is that you may not be at the assumed position. It's very unlikely that you were. I don't think I ever was. You are some distance either farther away from it or closer to it. How do you know? Well, the same math tables that gave you this angle also gave you the sextant reading you would have gotten had you been at that position. In this case, we'll say 34 degrees, 15 minutes. Of course, what you actually measured was somewhat different, 34:20. There's a 5-minute of arc difference between the two. That's called the altitude intercept, and it's greater. You had to be 5 miles closer to Regulus than the assumed position in order to get that measurement with your sextant. And so you lay off the altitude intercept for 5 miles, draw your line instead of a curve. Remember, we can approximate the curve with a line because it's so gentle. And that is the circle of equal altitude. We've now drawn it on our plotting sheet and drawn it accurately. And we are somewhere on that line. Okay. We'll take a quick look here at what we've done. We've used the trig tables. We've got the latitude and longitude of the assumed position, latitude and longitude of the geographic position, and we got out the azimuth and the computed altitude, which we compared with the measured altitude. This is what the navigation tables look like. This is the cover of the most frequently used ones back when I was doing this. This is what goes on inside of it, if you want to know this horrid expression for the computed altitude and for the azimuth. We'll get away from that quickly. This is a typical page that you use to look these things up. This volume contains 400 pages, and it is one of 6 volumes. So this is a rather large set of books to do your calculations. Okay, let's suppose that when we measured Regulus and went through the math, we got a we got our assumed position here, and the azimuth that came out with was 214 degrees. So we draw the line on the plotting sheet. There's the assumed position. This is toward Regulus. This is away from Regulus. Okay. The next thing we got from the math tables was the computed altitude for Regulus, in this case 3441. And if you subtract one from the other, you get an altitude intercept, a difference between the computed and the observed, of 6.1 minutes of arc, or 6.1 nautical miles. So you lay off the 6.1 miles, but in your perpendicular, there is your circle for Regulus, and you're somewhere on that circle. Okay, you need more than one body to get a fix, and let's say that we have measured Capella. The only way we can get those 2 measured at the same time is to be at their intersection. Maybe, because you measure more than 2 bodies, typically 5 or 6 if you can. Let's say that we also got a full house, and notice that we didn't really get a point, a pinpoint. We got a little error triangle here on our position, we're going to call it, is in the middle there. If that's on the order of a nautical mile, you're doing really well. If it's 2 or 3 nautical miles long and wide, you're still doing real well. You can do much worse in rough weather. But that effectively is your fix.
Rex, I'm gonna have to ask you that. We're wrapping up. You got a half hour already.
Oh, I'm sorry.
Yeah, we have one more guy, and everybody's really racing to get home. Can you wrap it up? It's very
Yeah,
simple.
yeah.
We all got
Well,
it.
that's really the end of it. That's all you need to do to get a fix.
Sure.
But if you want to do it at your telescope, record the time and the elevation and play around with it.
If you had a friend with a yacht, give him a hand. Actually, if you had a friend right now who wanted to go to Hawaii without any electronics, could you get him there?
Yeah.
Okay, we know. We also have a friend in Ojai. Thank you for coming, folks. And good luck to you. Thank you. Very well done. Here is your priceless piece of porcelain.
Oh, thank you.
Our thank you.
Yeah, this took considerably shorter with jabbering to Susie.
I know it did, because you were just jabbering to your wife. Thank you for coming.
One more show.
We- This is the icing on the cake. I wanted to briefly introduce Bruce Murdoch. Raise your hand, Bruce. He is president of the Theater Organ Society. If you really like to hear those organs, that big one in the stage down at the Arlington, check with his company. He's also part of our Monday morning podcast at 11 a.m. Okay, President Jerry is still on the screen, and here comes my man, Mike. Come on up, Mike. He's an astrophotographer with his son, Michael the third, I think it is. Been a member since 2012, has made astronomy a family hobby and acquired several telescopes using a wide field of objective lenses. They found some beautiful cosmic targets. The only way this is going to look any better is if it's on the ceiling of the planetarium.
Right.
So ladies, a big hand from Mike Hardwick.
Thank you.
Astrophotography.
I hope so.
Yeah, give him that. Okay.
All right.
Well, anyway, the Baron, the Baron said it well. We started 2012, my son and I, doing, actually started here with telescopes, and we went through the whole gamut, buying different telescopes, realizing somewhere along the line that looking through a telescope is actually an exercise in capturing light. And the better you can capture and the more light you can capture, the more you can see. And so we moved along, working our way through good quality lenses and getting to the point to where the next problem we had was finding the target. You can do the manual thing, you can do the sighting, but I was never any good at that. And my son realized that we could hook our telescope up to a cell phone with an astronomy app and actually select the location of these things and get the telescope pointed, because the telescope had a mount and it interfaced with the cell phone. So that was the next jump, to be able to selectively move our telescope to the target and then visually see it with good quality lenses. Problem was, if you were lucky, you'd see a nice picture, the spot of light or whatever it is in the location that you were looking, but you didn't see much. And then if you did see it, you didn't have a way of capturing what you saw. So somewhere along the line, about 3 years ago, I got with my son and I said, what do we need to do to make this interesting hobby? And he said, well, why don't we start doing, he's a cinematographer. He works for the movie industry. So he said, we should film it. And he said, we should get into astrophotography. Well, that's fine. So what is the equipment? It turns out that this whole industry, this astrophotography industry now has become a hobby, and the equipment to support that hobby is phenomenally changing at a phenomenal speed. So what I'm going to show you tonight is the telescopes, and then what we saw with the telescopes. Now, our first configuration here was a 5-inch refractor telescope, a 4.9 refractor. You can read that. Good quality lenses, the whole bit. We had actually purchased, we got ourselves a computer, the red box you see on top of that, and it drives the mount, which is the telescope is mounted on, and the scope off to the side left, that's a guide scope. It's got a camera, and all of this feeds into mount, the guide cameras and everything else feeds into a computer. The computer is the ASI Pro computer. The computer is driven with a cell phone. You can sit there and call this, bring up an application, pick your target. It transmits to the computer, and the computer then drives the mechanisms to get on target. The only way initially we had to image this stuff was with a single an SLR single lens reflex camera, which is what you would think you'd use. We found out that the problem with that kind of imaging, where our exposures were limited to 3 minutes, you had to use an ISO for you camera freaks of between 1600 and 3200. We couldn't use filters. Camera was not managed by the computer, and images had to be manually taken, had to set multiple clicks, and it had a battery limitation. When the camera ran out of battery, then you weren't taking pictures anymore. So this limited us. Now, what we were doing with these images, we're taking multiple images at about 3 minutes apiece, And then the next process is to take those images, stack them, and then create a multiple image light show photograph. And then we would do that with post-processing in a computer. There are computer programs that do that kind of thing. So that's how we started with our astrophotography. And it wasn't too bad. We were able to get some pretty good shots. There's the Orion Nebula, 64 1-minute exposures stacked. And you can see what it looked like. Here's the same thing. The 42.
Towards
Oh,
the
I'm sorry.
microphone, this area.
Yeah, 42 minutes stacked. All right, well, then we proceeded from there to get a little more sophisticated. My son was the techie, okay? I was the money bags. So what I would say to him is, what do we need to do this job? And how do we photograph the sky? Well, it turns out there isn't one telescope that does it all. So we wound up with 3 different types of telescopes. This one, the first is a wide angle Raptor 61 wide field. And it was like if you go look at the Scorpio, Rho Fuji, that area, if you're seeing that in dark sky, there's dust clouds that come all the way down to the horizon. So there's a whole wide area that you needed to film. So we decided to go ahead and splurge and go for that. So anyway, there's the camera, the camera, and the camera now is changed. The red can on the back is a 16-bit red, green, blue, 1-shot color camera designed for astrophotography. So now we're no longer using an SLR. We're now using a chip. It's incredibly large for what we're doing. And it's cooled. It has to be cooled to eliminate the noise. So it's got a little refrigerator in there. And that now is being fed to the computer. And so now the computer is driving everything. It's driving the camera, it's driving the guide scope, it's driving the mount, and we use the cell phone to pick the target. And these scopes are pretty good. I mean, the lenses are they've got flatteners in them, and we also can put filters in and that sort of thing. So now we're getting a little bit more sophisticated, and now you can see what that weight. That rig, now that it's been optimized with carbon legs and all that stuff, 20 or 30 pounds. I mean, all the stuff it was designed to be portable, because we found that if you're really going to take good pictures, now all this is being done in his backyard in Thousand Oaks. But if you really want to take good pictures, you need to get out to dark skies. And so we wanted to make this stuff portable. Anyway, this Raptor really produced some pretty good results. As you can see, there's Orion. Here's the North American and Pelican nebulas. And you can see now keep in mind, I got to explain this. Our camera is shooting RGB, red, green, blue, right? For pixels, kind of like what your TV does. All right. But but that doesn't match what you're watching. So if you use filters on your camera, you can then selectively pick the light that's coming from your nebulas and associate them with red, green, blue. So you can change the color palette, and you can start picking out sulfur, hydrogen alpha, oxygen, and that sort of thing, and shift it. And so with the use of filters and then plugging it into the camera, we're able to get close. We're able to differentiate the various gases that are in these nebulas. What we're mostly visualizing is what we call reflection nebulas. A reflection nebula is like a neon bulb. You need something to fire it off. Well, these nebulas that are sitting out there, reflection nebulas, have what they call an ionizing star associated with them. And those stars will light up that image. And then you're sitting down here with your filters and your cameras trying to capture that. and capture it over a long period of time so you get as much light as you possibly can. And now we're starting to see some pretty spectacular images. Here's another example, California Nebula. This was taken in Sedona. Here's a Sator region in the Cygnus area, 64 5-minute exposures. See the differences in color? This, and you see the yellow, which is the sulfur, the blue, which is an oxygen. So you begin to differentiate now what's actually in those nebulas based on your equipment. Okay, we wanted to jump up a little bit further, get a better scope. So as Chuck probably knows, because I think he has about a 4 or 5 inch telescope, it's kind of the mother of all telescopes. It's the sweet spot in a telescope. So we went for that. This is going to let us punch in a little closer. This is a 952 millimeter 5 inch f7.5. F-stop is like a camera. Smaller the number, the more light you get, and that comes in with your shooting. And so the object is to lower that f-stop. Get it as low as you can. That's called a fast telescope. When you get a lower f rating, that's a fast telescope capturing a lot of light for whatever image you're taking. So this thing started out as 7.5, but then we put a little some more gewgaws on there, and we got the f down to 4.9 by just putting some correcting lenses and sort of, so that made it a little bit faster. And it's an APO scope, so the lenses are high contrast for high contrast images. So we're refining our optics to try to get good quality shots. We're using the same computer, the ASI computer. We're using the same, that big can on the back that you see there standing up. That's an automated filter drawer. So we can selectively in the computer switch filters and through the whole thing. Keep in mind that what he does with this thing is he goes out with his cell phone. He picks his target. They give you suggested targets. There's an app that goes with this computer. And then you range in what it is you want to do. You pick your how many shots you want to do. You set it and go, and then he goes to bed. And this thing sits off and goes, it runs 2 or 3 hours. It starts clicking its way through the sky, taking these pictures. And then after it's done, he pulls off the images, and then we run them through a post-processing computer program called PixInsight, which helps us to go even further in modifying our images. And now we're looking at different, now here's Orion, and you can see the color differences. You can see the dynamic. This thing even has a face in it. Take a look at that arrow. If you really take a good look, you can see there's something living in that thing up there. I don't know how to go back.
The bottom arrow goes back.
Okay, here's some more things. The Cone Nebula and the Christmas tree cluster that's up there. You can see now the colors that are coming out. Listen, these things, we get this 16-bit camera produces these beautiful images, and I've been taking these things and making canvas prints of them, great big ones. And my wall now is covered with wallpaper and of these images, and it's amazing. I mean, it's almost like it's like modern art, only it's better than that. And so anyway, here's an example from that telescope. You can see the difference. The Rosette Nebula is next to it. Here's the Western Veil Nebula, looks like a seagull. 35-minute images stacked. Notice in this imaging all the stars that are behind it. A lot of times you'll get one of these nebulas and it's all the stars are behind it, and there's so many stars that you really can't see the nebula very well. Well, when you do post-processing through PixInsight, he can now take that back star pattern, remove it from the image, and then color enhance and work on bringing out the image and then add back the star pattern. He can even reduce the star pattern. So when we're done, we get something that looks a little bit better, like the Eastern Veil here. And you notice you're looking at almost all nebula and not too much in behind it. Yep, back. Okay, so I was telling you on the left, this is the Scorpio area. You can see Antares, the heart of the Scorpion there, and the stars that pop out on the right, the Lagoon and Triad nebulas. See how these images are starting to pop. Going the wrong way. Okay, now, interesting. Here's the Dumbbell Nebula. All these things have names, generic names. They have IC numbers, but you get to know them by their generic names, like Dragon, Horsehair, or whatever, all these different nebulas. This one over here on the right, very interesting. This is Sirius, and look at the bubble that's around it. Remember a couple of last session, we had the guy was telling us about how stars can produce bubbles of gas, and they could create these what do they call them? Bow shocks. I'll show you a good bow shock. Anyway, this is kind of what's happening in this area. Never would have seen it if we hadn't done what we were doing with, with these telescopes. Cygnus Wall area, Cave Nebula, the Wizard Nebula on the left, the Pac-Man Nebula, if you can believe it. All these, and you got to look at these things and you go, yeah, it kind of looks like a Pac-Man, All right, now this is the big gun. This is our last investment. And so it's a Celestron 11-inch, Schmidt Cassegrain. But some time ago, we went to Arizona in Arizona, and they had come up with this hyperstar arrangement where they take the lens or the secondary mirror off, and instead they stick on this hyperstar lens in the front. So you actually got a big lens attachment now that is staring right down, at your mirror. And what that does is it produces a really fast, it takes it from like 25, F25 or whatever it is, down to F.1.9. And this makes for a really fast telescope. And so again, now the other thing we've done is it's got a bigger range that you can look at. So we bought the camera, full frame camera to capture that range. The other thing that happens with this thing is it's very, very sensitive. So it's mounted on a pier mount that's fairly strong to hold it, because any vibration will affect what you're looking at. And you gotta kind of tune it and optimize it and keep it that way. Once you get it there, then it's good to go. And he leaves it set up and we keep shooting from there. But anyway, so this crazy thing, it's got everything else. It's got this, it's the cameras, the guide scopes, and all that stuff. And Hyperstar, which has made all the difference in the world. Now we're looking at Andromeda. Is that Andromeda or is that Andromeda? That's taken with Hyperstar. On the left is the Gamma Cast Nebula, and look at the star Navi there that pops out at you. These two nebulas would never have been captured with the other scopes. And we just got them this year, the Witch Head Nebula and the Flying Dragon Nebula. These are very faint, hard to see, but Hyperstar with the Celestron made all the difference in the world. So you can see what we're visualizing there. Here's some more, the jellyfish you saw before. The only problem with this arrangement is since you're looking directly at the mirror, your image comes out inverted. Like you're looking in a mirror, because you've got a lens that's peeping right down at the mirror. Well, he can fix that with post-processing. He flips it. But so this is the Jellyfish Nebula, and the processing of the palette. You can see the differences. the image below was taken with RGB before we put filtering on it. And the image above is now with filtering. And now we have the SHO palette, or the sulfur, hydrogen, oxygen. So we change, literally in post-processing, change the colors of the nebula that we're looking at, and get colors closer to the gases that are being, that the images, that these images are producing. Now this is the last one. This is the ghost of Cassiopeia. Here down at the bottom, you see the star Gamma Cassiopeia. It's a blue-white variable star, 65,000 times brighter than our sun, and 19 times more massive. I think our last talk talked about these massive stars, and that's an example of one of them. Over here, this was the latest one. We got the Seagull Nebula. If you look at it, it kind of looks like a seagull. But check out right, see that? I don't know. At the bottom. Oh.
Yeah, there you go.
There it is. That's what did you call that?
Bow shot.
Bow shot. There is an example. Remember the guy had pictures last time of a bow shot, a bow shot, whatever it is. Well, there is a really good example of one right there in that nebula. And if you look around, there are other stars up there that have similar kinds of bow shocks involved with it. So we've had a lot of good luck with this equipment, and that's pretty much it. Now, in case any of you are interested in doing astrophotography, I have brochures up here that you can take home.
Most of the images shot in Melbourne.
Right in his backyard.
And that's.
Yeah, right there. And you know, I was sitting there the other night in the backyard with him, and he's got all these telephone wires that run across the, his yard. And I said, how in the hell do you avoid those telephone wires? He says, I shoot right through them. They don't even show up. Because the camera's like sitting up here, the mirror is back here, and he's just, going right through these darn things. And he's getting some beautiful images from it. So anyway, I could go on forever, but
You did good.
there you go.
That's good. Thank you. My man Mike. He's also as historian, written some books about Spanish history and some missions. And if you really want a good place to go with great light, try Rex Meach's house over in Ojai.
Yeah. Just have to drive the equipment up there.
We got a new board, at least 2 new members, and we've reelected the vice president and the president, and we'll hope to see you back here, next Saturday night for Star Party, and next month when we talk about an incredible place back in Springfield, Vermont, called Stellafane. Look it up. It was one of the first astronomy clubs in America, and they've been grinding for a year, grinding lenses. Did you have a question, ma'am? First Friday would be the 5th, I think, isn't it?
Oh, yeah.
I think it is, yeah. Try to come over the hill. Thanks, everybody, and we'll see you next month. Good job, Ron. Good job. Thank you. Good.
Good to
I
ring
say
that
it both
second guy.
to you too, man. It was awesome. Very few problems.
Bye, Jerry. Talk to you later. The sound was better with using the sound off the camera instead of the laptop. That's what changed. All right, ending the show.
Thanks, Jerry.
Meeting for all.